Hey everyone, welcome to the brand new series dedicated to GCSE Computer Science 9 to 1. Whether you're just starting out or aiming to boost your grade, this series is here to help you master the content and get the top grades that you deserve. In every video, we'll break down key topics, walk through clear examples, and share expert tips to make sure you're exam ready. But wait, there's more. After each lesson, stick around for YouTube shorts packed with exam-style questions and answers to test your knowledge and lock in what you've learned. Make sure you press the subscribe button and turn on notifications so you don't miss a thing. Let's unlock those top grades together. Ready? Let's dive in. So our first video today, we're going to explore the architecture of the CPU. If you've ever wondered how computers work or what makes them so fast and powerful, you're in the right place. So by the end of this video, you'll understand the key components of a CPU, how it processes instructions, and why it's often called the brain of the computer. Let's get started. Before we dive in, let's take a quick look at what you learn in this video. So by the end, you'll be able to describe the basic components of a computer system, explain the purpose and function of the CPU, understand the fetch, decode, execute cycle, identify and explain the key components of the CPU, compare and contrast primary and secondary storage. These are the key takeaways, so keep them in your mind as we go through the lesson. Let's start by talking about what a computer system actually is. A computer system is made up of two main parts, hardware and software. Hardware is the physical stuff you can touch, like your keyboard, mouse, or screen. Software is the programs that run on the computer, like games, apps, or even the videos you're watching right now. Now, computer systems are everywhere. They're not just the laptops or desktops you might be used to. Think about your smartphones, the cash machine at the bank, or even the system that controls the engine in a car. All of these are examples of computer systems. They all have a CPU, memory, and input-output devices, which we'll talk about next. Every computer system has four basic components. Let's break them down. The first are input devices. These are things like your keyboard, mouse, or even a microphone. They take real-world data and convert it into a form the computer can understand. The second is a processor, or the CPU. This is the brain of the computer. It processes the data and instructions. The third is the memory, or primary storage. This is where the computer holds the data and instructions it's currently using. The fourth are output devices. These are things like your screen, printer, or speakers. They take the processed data and turn it into something you can see, hear, or use. There's also a fifth component called secondary storage, like a hard drive or USB memory stick. This is where computers store data long-term, like your photos, videos, or school projects. So to sum up, input devices send data to the CPU. The CPU processes it, and then output devices show you the results. Memory and storage help the computer keep track of everything along the way. Now, let's focus on the CPU, or central processing unit. The CPU is like the brain of the computer. It is responsible for fetching, decoding, and executing instructions. Think of it as the part of the computer that does all the thinking and decision making. The CPU has three main parts: The control unit, which is like the manager of the CPU, it controls the flow of data and instructions, making sure everything happens in the right order. The arithmetic logic unit, or the ALU. This is the part that does all the math and logical operations, like adding numbers or comparing values. Registers. These are tiny, super fast memory locations inside the CPU that temporarily hold data while it's being processed. So the CPU is where all the action happens. It takes data from memory, processes it, and then sends the results back to memory or to an output device. Now, let's talk about something called von Neumann architecture. This is a design for computers that was developed by a scientist named John von Neumann in the 1940s. Before this, computers couldn't store programs. They had to be manually input every time, which was really slow and inefficient. Von Neumann's big idea was to store both the program instructions and the data in the same memory. This means the CPU can fetch instructions and data from memory, process them, and then store the results back in memory. To give you an analogy, think of a recipe book. The recipes, or the programs, and the ingredients, which are the data, are all stored in the same book. The CPU is like the chef who reads the recipe, gathers the ingredients, and then cooks the meal. This design is still used in almost all computers today. Now, let's talk about how the CPU actually processes instructions. It does this through something called the fetch, decode, execute cycle. This is a three-step process that the CPU repeats over and over again to run programs. Here's how it works. The first, which is the fetch stage, the CPU fetches the next instruction from memory. The second, which is the decode stage, the CPU decodes the instruction to figure out what it needs to do. The third, which is the execute stage, this is where the CPU carries out the instruction, like adding two numbers or moving data. To give you an example, imagine you're following a recipe. First, you read the next step, which is fetch. Then you understand what to do, which is decode. And finally, you do it, or you execute. The CPU does the same thing, but it does it millions of times per second. Let's take a closer look at the components inside the CPU. The control unit, this is like the traffic controller of the CPU. It makes sure instructions are executed in the right order and controls the flow of data. The arithmetic logic unit, or the ALU, this is where all the math and logic happens. It can add, subtract, multiply, and even compare numbers to see which is bigger. Registers. These are like sticky notes for the CPU. They're small, fast memory locations that hold data temporarily while it's being processed. So the control unit manages everything. The ALU does the calculations, and the registers hold the data. Together, they make the CPU work. Let's talk about registers. These are special memory locations inside the CPU that are used to hold data temporarily while it's being processed. There are a few key registers you should know about. The MAR, or the Memory Address Register, This holds the address of the next instruction or piece of data to be fetched. The MDR, or the Memory Data Register, this temporarily holds the data that's been fetched from memory. The Program Counter, or the PC, this keeps track of the next instruction to be executed. And the Accumulator, or the ACC, this stores the results of calculations done by the ALU. Think of registers as the CPU's notepad. They're used to jot down important information while the CPU is working. Let's look at an example of how the CPU executes instructions. Imagine the CPU needs to add 80 to a number stored in memory. Here's how it would do it. The first stage is the fetch stage. The CPU fetches the number from memory. The second stage is to decode. The CPU decodes the instruction and realizes it needs to add 80. The third stage is the execute stage. The CPU performs the addition and stores the result back in memory. In a programming language like Python, it might look like what you can see on your screen. A equals A plus 80. But in assembly language, which is closer to what the CPU understands, it would be broken down into smaller steps like load the number from memory, add 80 to it, store the result back in memory. This is how the CPU processes even the simplest of instructions. Now let's talk about what makes a CPU fast or slow. There are three main factors that affect CPU speed. The clock speed. This is how many instructions the CPU can process per second. It's measured in gigahertz. A higher clock speed measures a faster CPU. The second is the cache size. This is a small, super fast memory inside the CPU that stores frequently used data. The bigger the cache, the less time the CPU spends waiting for data. The third is the number of cores. Modern CPUs have multiple cores, which are like having multiple brains inside one CPU. More cores mean the CPU can do more tasks at the same time. To give you an analogy, think of the CPU as a chef. Clock speed is how fast the chef can chop. Cache is the chef's prep table. The cores are like having multiple chefs in the kitchen. The more chefs you have, the faster you can get the job done. Let's look at embedded systems. These are small computers designed for specific tasks. They're not like your laptop or phone, which can do many different things. Instead, embedded systems are built into devices to control them. Examples of embedded systems include washing machines, traffic lights, smart thermostats. Think of an embedded system as the brain inside your microwave. It's not a full computer, but it controls the microwave's functions, like setting the timer or adjusting the power level. Embedded systems often use simpler CPUs because they only need to do one job really well. Now, let's talk about primary storage, which is the memory the CPU uses to store data and instructions while it's working. There are two types of primary storage. RAM, which stands for random access memory. This is temporary memory that loses its data when the computer is turned off. It's used to store data and instructions that the CPU is currently using. ROM, or read-only memory. This is permanent memory that stores essential instructions like the BIOS, which helps the computer start up. To give you an analogy, think of RAM as a whiteboard. You can write and erase it as needed, but when you turn off the computer, the whiteboard gets wiped clean. ROM, on the other hand, is like a printed manual. It stays the same, even when the computer is turned off. Sometimes the computer runs out of RAM, especially if you're running lots of programs at once. When this happens, the computer uses something called virtual memory. Virtual memory is a section of the hard drive that acts like extra RAM. The downside is that virtual memory is much slower than RAM because hard drives are slower than memory. Think of RAM as your desk, where you keep the papers you're working on. When your desk gets full, you store some extra papers in a filing cabinet, such as your virtual memory. It takes longer to access those papers, but at least you have more space to work. Let's talk about secondary storage. This is where the computer stores data long term, even when it's turned off. There are three main types of secondary storage. Magnetic storage. This includes hard drives, which are cheap and can store a lot of data, but they're slower and less durable. Optical storage. This includes CDs and DVDs, which are portable and cheap, but they have limited capacity and can be easily damaged. Solid state storage. This includes SSDs and USB drives, which are fast, durable, and portable, but they're a little bit more expensive. Think of secondary storage as a library where you store books, such as data, for use later on. You can't keep all your books on your desk, which is like your RAM, so you can store them in the library, which is your secondary storage, and bring them out when you need them. Let's compare the different types of storage. Each has its pros and cons. Magnetic storage has high capacity and low cost, but slower and less durable. Optical storage, such as is portable and cheap, but limited capacity and easily damaged. Solid state storage is fast, durable, and portable, but more expensive. Choosing the right storage is like picking a backpack. Magnetic storage is like a big bag. Magnetic storage is like a big, cheap backpack. It can hold a lot, but it's heavy and not very durable. Optical storage is like a lightweight backpack. It's easy to carry, but it can't hold much and it's easily damaged. Solid state storage is like a sleek, high quality backpack. It's fast, durable, and portable, but it's more expensive. Let's quickly recap what we've learned. The CPU is a brain of the computer, and it follows the fetch, decode, execute cycle to process instructions. It has three main components: the control unit, the arithmetic logic unit, and the registers. The von Neumann architecture stores both programs and data in memory, which is why modern computers are so powerful. Factors like clock speed, cache size, and cores affect CPU performance. Primary storage, such as RAM and ROM, and secondary storage, hard drives, SSDs, are essential for storing data. I hope this has helped you understand how the CPU works and why it's such an important part of everyday computer system. Pause the video and have a think about these questions. If you're not sure, go back and rewatch the relevant parts of the video. And don't worry if you don't get everything right away. This is complex stuff, but you're doing great. This brings us to the end of our video. Thanks for watching. If you found this video helpful, don't forget to give it a thumbs up and share it with your friends. And if you have any questions, leave them in the comments below. I'd love to hear from you. Make sure to subscribe for more educational videos like this one, and I'll see you next time. Bye for now.